Good morning, organic chemists. Happy Friday. We made it to the end of our first week. We did it. Good job. All right. So, first announcement, Chemistry Club. We'd love for you to join us. We're just going to do virtual stuff, obviously, like every other club on campus this semester. So we'll have a bunch of fun things that we're going to be doing, like game nights. We are going to continue our mentorship program. So if you're a chemistry major and you'd like to mentor someone, or if you'd like to be mentored by someone who is more advanced, then let us know. We'll also be doing virtual study sessions. So um, you see the QR code there, so you can sign up, or you can sign up on Inside CBU, or you can just email me if you're interested. Also, if you're interested in being an officer in Chemistry Club, you can also email me about that because we do have some officer positions available. Then our next announcement, make sure that your name is entered correctly on, what is this? No, WebEx. We had our office hours this week. We have a few more office hours today. So if you have today's office hours, make sure you show up. I know some people missed their times this week, so let's not miss any times next week and going forward, because these are your weekly office hours. These are your chances to get everything, all your questions answered weekly, rather than, kind of never saying you have time. Now you have time, it's set in your schedule. Make sure you have your cameras on right now. And then this is your last chance to watch those videos. After this weekend, if you don't watch those videos, and I mean actually watch them, then you will be losing points. So make sure you watch the videos, the course introduction videos that are in on the announcements page. So make sure you've actually watched them, because as I said, I can see how much of the video you've watched. And if you haven't watched the whole thing, then you're gonna lose points after this. So if you didn't watch them, please watch them. Some people are asking me questions that I know were answered in the video, and so that tells me that you didn't watch it. So this is your chance to actually watch it and not lose out on those points. All right, let's move on. We are talking about our alkene properties, and we said for the alkenes, we talked about the dipole, right? We said that we could pull away electron density because the alkene has so much S character. The alkene carbon has the S character. We can pull electron density away from the carbons bonded to it, but we can also pull electron density away from hydrogens bonded to the carbon. So here, this carbon's going to have partial negative, and this hydrogen's going to have a partial positive. What happens if we make hydrogens partial positive? Well, we make them acidic, right? And so that hydrogen is slightly acidic. So we have alkane hydrogen versus alkene hydrogen. We're looking at the acidity of it. Well, for this, the pKa is going to be 50. So you see the K is 10 to the negative 50. And then here the pKa is 44. So which one is a stronger acid? Remember, the lower the pKa, the stronger the acid is. So obviously the alkene is going to be the stronger acid. But look at this number, 44. It's still a weak acid overall. So if we're just comparing alkanes and alkenes, the stronger acid is the alkene. But if we're comparing alkenes to sulfuric acid, which has a negative value for the pKa, you remember that that's going to be a really strong acid with the negative value. So this is still, these are weak acids, but it is a stronger acid than alkane. And so when we are deprotonating, remember we have some kind of a base, so negative charge coming in, taking this proton, and then the electrons go to that carbon. And so we end up with this lone pair on the carbon. Let's move the negative charge because it's on the carbon, it's not on the hydrogen. But remember that that carbon now has a negative charge, and we've made now an anion, this vinyl anion. So alkenes are weak acids. They can be deprotonated in the presence of a really strong base. Questions there? All right. So now get out your NMR IR sheet because we're going to talk about spectroscopy now. And you might want to make some notes on that. Remember, we said we're going to have that close to us all the time. So for proton NMR, when we're talking about alkenes, we have these two values here. So terminal alkene, internal alkene. Whether this is saying the hydrogens are on the end or the hydrogens are kind of more internal. It's not necessarily meaning that the whole alkene has to be a terminal alkene or the whole alkene is an internal alkene. We're talking about really where the hydrogens are. So when the hydrogens are on the very end of an alkene, then we're going to see the values at about 4.6 to 5. When they are more internal, then we would see the values at 5.2 to 5.7. But in both cases, we know that these are de-shielded, downfield, because, why? Because these are hydrogens on an sp2 hybridized carbon, just like what we were just talking about, right? That sp2 hybridized carbon is pulling away electron density from those hydrogens, making them acidic, but also de-shielding them, removing the shield of electrons. So these hydrogens get de-shielded because they are next to an electron withdrawing group. That carbon that is sp2 hybridized is an electron withdrawing group. So we see that alkene hydrogens, the hydrogens directly bonded to the carbon that is sp2 hybridized, those are going to be de-shielded. And then we also have this other value called allylic. So remember when we were talking about the alkenyl substituents, we said that if we had this substituent, here where we have a double bond on the end here, that we could call this allyl. And so we had a CH2, and then we had two carbons that had a double bond, so 2-propenyl. But we said 2-propenyl had another name, which was allyl. And so now we have something called allylic, which means really this carbon. This carbon is the allylic carbon. And so the allylic carbon is directly beside a double bond. So we have an alkene here, and then we have a carbon right beside that double bond. On that carbon, right beside the double bond, those hydrogens are going to be de-shielded. They're not de-shielded as much as if they were directly attached to the sp2 hybridized carbon, but if they are on a carbon right next to a double bond, then we see them showing up a little bit downfield, 1.6 to 1.9. So now we have these three values we have to look at: allylic, terminal alkene, internal alkene, as we are studying these different alkenes. So allylic just means it is the carbon or the hydrogens next to the double bond, not on the double bond. Questions there?
Oh, sorry, Dr. Nalbandian.
Go ahead.
Which one did you say was the internal, and which one did you say was the terminal? Oh, wait, they say it there. Never mind.
Yeah, you're fine.
One more time. The allylic, you said carbon and hydrogen next to the double bond.
Yeah, so anything here, so what I have up here, carbon 1 is an allylic carbon, and the hydrogens on carbon 1 are allylic hydrogens because they are right beside a double bond. Whereas hydrogens that are on carbon 2, those would count as being terminal alkene, and the hydrogens that are on carbon 3, those would be, sorry, I said that wrong. What's on carbon 2, the hydrogen on carbon 2 would be internal, and the hydrogen on carbon 3 would count as terminal based on what's in this table. Even though it's not a terminal alkene, even though it's not an internal alkene, these are internal alkene hydrogens. That's what the table is more so saying. All right, so let's look at an NMR. So here we have 2255 tetramethyl 3-hexene. When we look at this, we can see that it is trans because the two T-butyl groups are trans to one another. But looking at this molecule, we also can see that there is symmetry here. And so remember from lab this week, from our refresher, we talked about, well, you should have talked about in your group, how symmetry means that these things are going to show up in the same exact place, right? All these things are chemically equivalent. So if we look at what's attached here to this carbon, on that carbon, any of those methyls are going to be chemically equivalent to each other. So these 3 hydrogens are equivalent to these 3, are equivalent to these 3. So all 9 of those are equivalent to one another because they are all attached to the same carbon. And on the other side, we have a mirror image of that. So based on the symmetry, these 3, and these 3 are also all equivalent. So they all show up here. All 18 of those hydrogens, remember this is the integration, all 18 of those hydrogens show up in the same spot. Now what is this? CH3,4. Remember that is our tetramethylsilane. Our TMS, our internal standard, shows up at 0. So we have those 18 hydrogens that are not allylic. These are not allylic hydrogens. Why are they not allylic? Well, because here is our double bond. If they were hydrogens on this carbon, then they would show up as allylic, but they're one more carbon away. And so they're not allylic. They're showing up where we would expect these hydrogens to be. So then we look, we have these hydrogens that are directly bonded to an sp2 hybridized carbon, so they are de-shielded. The carbons that are sp2 hybridized are pulling away electron density. They are both showing up in the same place, and so our integration is 2 hydrogens. And we look where our chemical shift is. It's here, maybe about 3-ish. And so we can see that that is downfield, de-shielded, and we are seeing that because they are attached to this sp2 hybridized carbon, but they're both showing up in the same place because of symmetry. They are chemically equivalent to one another. So we can see the difference there in what is de-shielded, downfield, or what is upfield, which would be here at 1, upfield, these 18 hydrogens, because they don't have anything really pulling away electron density. So when we have that symmetrical alkene, all the protons on the alkene were equivalent. But what happens if it's not symmetrical? Then we have different protons there. Now the protons are going to show up in a different place. They're not going to all show up in the exact same place. So we can use our coupling constants. So remember last semester we talked about coupling constants, these J values, and we said they were going to come in handy in the future. This is where they come in handy. So for a J value, remember, that is telling us how much the peak is split. So remember we have our splitting. So let's say a peak is split into a triplet. So if the peak is split into a triplet, remember that we would get this triplet. And so the J value here is how much this is split. This is our J value. How much splitting we're seeing in that peak. So this would be a small J value versus this, where this would be a large J value. So we get these different J values. If the hydrogens are cis to one another, now this is important, cis to one another, then we usually get a smaller J value. If they are trans to one another, then we get a larger J value. So what is important here? That it's cis to one another, trans to one another. I'm not saying that it is a cis double bond or a trans double bond. I'm saying that the 2 hydrogens are cis to each other or trans to each other. So here we do see a cis double bond and a trans double bond, but that's not what we're exactly talking about. And I'll show you more of this in a minute. But just know that that's not exactly what we're seeing here. It doesn't have to be a cis double bond. It has to be that the hydrogens are cis to one another. So here, these are hydrogens cis to one another. Versus on the other spectra, we have hydrogens that are trans to one another. So their environment, their chemical environment is different. Remember, this is a double bond, and with the double bond, we don't have rotation. If this was a single bond, we could rotate around where there would be no difference. But because it's a double bond, it's locked into place, trigonal planar, so we don't have rotation, so we can either have the hydrogen cis to one another or trans to one another, but we can't rotate around like we could when we had single bonds. So when we're looking at this now, we can see the J values are giving us some information. So the J value of 9 versus the J value of 14, as I said, the J values are smaller when it is a cis coupling versus when it is a trans coupling. We have a smaller value for cis coupling. And so we see the same value for both. So for the green hydrogen, we see a 9 hertz J value. For the pink, we see a 9 hertz J value. These two are coupled to one another, and so they're going to have the same J value. Green sees pink, pink sees green, and so they're going to have the exact same J value, 9 hertz, over here when they are cis to one another. If we switch over to the other spectrum where they are trans to one another, again, still green sees pink, pink sees green. And so again, they are trans to one another here. And so we're going to see the same exact J value for both, 14 for both, because they are both trans to one another. We see them both as doublets because if we're looking at green, green has one hydrogen neighbor, which is pink. And so with that one hydrogen neighbor, it's split into a doublet. We see the same thing for the pink. Pink has one hydrogen neighbor, which is green, and so it's also split into a doublet. Here we see our TMS just at 0. And then up here, we see something that we haven't seen before, really, because we haven't gotten to our carboxylic acids, which you did look at this week, where you see that broad singlet, where it is that OH. But here the OH is a carboxylic acid OH, which is different from an alcohol OH. But it's still going to be a broad singlet. So we see the broad singlet showing up in both of our spectra, but what's different here is the J value, that splitting of the peak, if the hydrogens are cis to one another or if they're trans. What's also different here is if we look at this 7 to 6 range, we can see that those peaks are showing up in different places as well, right? The peaks are going to show up in slightly different places, different chemical shifts for the two different molecules. So we know these are two different molecules. They're not the same thing. They're two different molecules. We have different J values, different parts per million, different chemical shifts there. So when it's an unsymmetrical molecule, so we see we have chlorine here versus a carboxylic acid, there's no symmetry here. We can't mirror anything. And so now we get these different values for the different hydrogens, and the hydrogens are coupled to one another. They're coupled to one another. So green sees pink. So they are being split by one another into doublets. So let me just go back just to remind you, here, these two hydrogens were trans to one another, but because of symmetry, there's no splitting. This is a singlet. There's no splitting here because they are the same. They're equivalent to one another, so they're not neighboring hydrogens. They're not going to split one another into a doublet, triplet, whatever. It's going to be a singlet, no hydrogen neighbors. Versus here, we do have hydrogen neighbors, so green can see pink as something different from it because pink's chemical environment is close to a carboxylic acid, whereas green's is close to a chlorine. So they are chemically different from each other. They're non-equivalent, and so they can now couple to one another. Questions on what we've covered so far?
I have a question. So if you see the 9 value for the J splitting, would you consider that small? Would you know that that's cis if you don't have another molecule to compare it to?
Right. So we're going to see a table on the next slide that'll give us more insight into that. But yeah, so here just relative to one another, this one's smaller than the other. But yeah, there is a table that gives us more like ranges.
Okay, thank you.
Uh-huh.
Question.
Other? Yeah.
So for as we're seeing that this is down kind of field, is this similar to how we did with the halogens? Like halogens are down in the field, are kind of like these.
Because something is close to a halogen, yeah, that's an electron withdrawing group. So these hydrogens, like green, is on an electron withdrawing group, this sp2 hybridized carbon, and it's also then by induction on the same carbon as a chlorine. And so yeah, green is going to show up further downfield than pink, because of the 2 electron withdrawing groups by induction. All right, so as I said, we have a table here where we can see ranges. Now, when you see cis here, this is cis to one another. It doesn't mean that it's a cis alkene. It means that these 2 hydrogens are cis to one another. When we see trans, again, that's trans to one another. So vicinal, meaning neighbor, neighborhood in the vicinity, vicinal, versus geminal, Gemini, twins, meaning they're on the same exact carbon. So when they're on the same exact carbon, now again, there's no rotation. And so when these 2 hydrogens are on the exact same carbon of an alkene, they're going to have different environments. What's over here is going to look different to what's over here. And so those 2 hydrogens are going to be different from one another. They are going to be coupled to one another. And so we're going to see a J value for that kind of coupling, where they're on the end of a terminal alkene. These 2 hydrogens are different from each other. They're both on the same carbon, so we call them twins, but they're twins that have different things that they can see. Their viewpoint is different. So we have our vicinal cis and trans in the vicinity of one another on neighboring carbons versus geminal on the exact same carbon. So for those, we can see we have these different ranges. This is very small here, obviously, these 2 being close together, but we have these typical values. So typically it's about a 10, typically it's about a 16, typically about a 2. So then we have this other thing where we have a hydrogen that is on a carbon of a double bond. It has to be on a carbon of a double bond, and it is coupled to a hydrogen that is beside it on another carbon. So we have an alkenyl hydrogen, and then we have a hydrogen that's beside it. So here we were talking about the 2 hydrogens of the alkene, side by side, neighboring carbons of the alkene. But now we're talking about alkene on one side, and then here, usually this is going to be something that's sp3 on the other side. But this is just called none coupling, and this would be 6. Then we have these 2. And so these 2 are called long range couplings. And so for these, on an exam or on a problem set, I will ignore these. But in the homework, they won't be ignored. And I want you to know that they exist as well. But I would ignore these long range couplings. And so really on an exam or on a problem set, I would just give you the first 4. Just because if I give you more, it kind of complicates things. But anyway, about these, look at this. 1, 2, 3 carbons away. We couldn't do this when we were talking about alkanes. Alkanes was just, what's the carbon directly beside it on all sides, right? 1 carbon away on all sides. But now we get this long range coupling through the alkene. So it's only because we have an alkene there. We can go from a hydrogen that's directly bonded to an alkene through the alkene carbons, through to a carbon on the other side to a hydrogen there. So this is called a allylic or 1,3 cis, 1,3 trans coupling, and it's a very small value, so that's why we would ignore it for the most part. But now this is long range coupling. Instead of one thing, so we have, let's say, 2 hydrogen neighbors over here, and so this is a triplet. We can go 3 carbons away if we go through a double bond. Here we can go 4 carbons away if we go through a double bond. If it's all single bonds, if carbon 2 and carbon 3 are have a single bond between them, we can't do this long range coupling. We can only do this long range coupling because we are going through this double bond. The double bond allows for us to have this long range coupling, so 1,4 or long range coupling. And again, this is really small. So most of the time, if the value is a 0.5 or a 0, think about this is how much the peak is being split. So if it's a 0, you're not going to see any splitting. You're not going to see that change in distance there for the peak. If it's 0.5, again, that's so small that you almost won't even see it. So that's why we ignore these long-range couplings. So let's look at this. So we have this table here. You have this on your IR NMR sheet. So hopefully you were looking at that. It's on the sheet there for you. So let's look at that in practice. So let's look at this molecule. So 3,3-dimethyl-1-butene. So for this, we have what they've labeled hydrogen A. So let's look at hydrogen A first off. So hydrogen A, it's going to be more internal, and so it's going to be further downfield. It's more internal. Even though the alkene itself is a terminal alkene, hydrogen A is internal, more internal in the molecule. So when they say internal on that sheet, they're saying more internal in the molecule. So it's more downfield. Anyway, so what does hydrogen A see? Well, hydrogen A can see hydrogen C, and they are cis to one another, right? Hydrogen A and hydrogen C are cis to one another. So we get this J value of 10.5 hertz. But hydrogen A can also see hydrogen B, and hydrogen B is different from C. B and C are different because they have different chemical environments. Look at B. B is close to a T-butyl group, but look at C. C is close to hydrogen A. So they have different chemical environments, and so B and C are different. So A can see C, and A can also see B. And so A and B, we get this trans because they are trans to one another. Notice that the alkene is not a trans alkene or a cis alkene. But we're saying that the hydrogens are cis to one another. The hydrogens are trans to one another. So A is trans to B. So we get a J value of 18 hertz. And A is cis to C. So we get a J value of 10.5 hertz. So for A and B, look at here. The peak for A gets split into a doublet because it has one hydrogen neighbor, which is B. A has one hydrogen neighbor, which is B, and so it gets split into this really large doublet. And so you can see the splitting there. That would be 18 hertz for that first splitting. But then each of the peaks that we split are split further into doublets, and so we get now another doublet here for each of those peaks. But now they're not split as far, right? Now they're only split 10.5 hertz. And so if we only get this 10.5 hertz splitting, then we're going to see that it's a little bit smaller than the first one. But for A is a doublet of doublets. A is split into a doublet by C. A is split into a doublet by B. A is a doublet of doublets. All right, let's do that same thing, but now we'll do it for B. So what does B have? B can see A. And so for B and A, again, we're still talking about this 18 hertz coupling. And so again, it's a doublet. And so if we look here, A and B, the first thing we see is that it's split into a doublet by A. B is split into a doublet by A, and we get this large 18 hertz splitting. But then B is now geminal to C. B is geminal to C, and that's a 1.5. It's a really small splitting. So look at this splitting here. It's almost something that we can't even see. It's so small that we almost can't even see it. But if we're looking at these green, so just the green, not the pink, if we're looking at these green peaks, we can see that they're split into a doublet, and then the top of the peaks are split into a really small doublet as well. It's not as pronounced as this, where we had these two large J values. Now we have a large one and a really small one. And so we get a doublet that's split into these tiny doublets on top, but it's still a doublet of doublets for B. Now we can look at C. So what does C have around it? Well, C can see A. It is cis to A. And so here, that would be AC 10.5 hertz. If we see it from one direction, we see it from the other direction, right? We saw that 10.5 hertz from the perspective of A. Now we're seeing 10.5 hertz from the perspective of C. So it's split into 10.5 hertz doublet, and then it's also split into an even smaller doublet. Each of those peaks are split into doublets themselves, based on C being geminal to B. And so we get that 1.5 hertz. So again, we have another doublet of doublets. So each of these are doublet of doublets, but look at, they all look different. They all look different based on these different J values, but they're all revealing, okay, this is what I can see. This is what I can see. They're all telling you what they can see. So with these J values, we're getting even more information than we did just by saying doublet of doublet, quartet of triplet of doublets, whatever. We're getting way more information here now, adding in these J values, because now we can see stereochemistry. Now we can see these two are cis to one another, these two are geminal, these are trans. Now we get more information. So finally, the last thing here, we have these nine hydrogens that are showing up here. Again, they are not allylic, and so they're showing up where we would expect, about 1. And then we have our TMS giving us a peak at 0. Questions on this?
Wait, so how does these Hertz values relate to the cis coupling, and then how do they affect if the peaks are like doubling and stuff?
How much the peak is split, that's what the J value is. So the J value is the distance that the peak is split.
Okay.
So if they are cis to one another, they are split, but not as much as if the hydrogens are trans to one another.
Okay, all right.
Is that what you're saying?
Yeah.
Okay. So then, yeah, geminal is small, and then the cis is larger, but not large, and trans is even larger, based on what we had in that table.
Okay, all right. Thank you.
Why does the blue hydrogen show 3 neighbors? It doesn't. Yeah, it's a doublet of doublets. It's not a quartet. It's a doublet of doublets. So sometimes in the textbook, they would call this a quartet when you're doing your homework, but know that it really is this. Even though it looks like a quartet, it's not a true quartet, because what does a true quartet look like? Small, medium, medium, small. That's what a true quartet looks like. And these are all basically the same height. All right. So know that in real life, this gets even messier. So if we look at this green hydrogen here, this green hydrogen is coupled. So we get geminal, we get trans, and then we can get that long range coupling as well, that allylic long range coupling. And so what we're seeing here is this really complicated spectrum, where now we also are seeing the other green. So the other green is also having this cis and now this long range coupling, but all that's showing up in the exact same place. We're seeing both of those hydrogens kind of overlapping here. Instead of being separated from each other where we can see them, now both of those geminal hydrogens are kind of showing up in the exact same place. And so we get this really complicated spectrum with all this splitting there. So it doesn't look really cute sometimes in real life. So when I'm giving you a problem, I'm going to give you things that are first order, but know that we can get this non-first order multiplet that's possible. Sorry. Non-first order multiplet that's possible in real life. But I'll try to give you things that are really nice, clear cut. Oh, thank you. Really nice and clear cut. I thought you were saying bless me for not giving you hard problems. I was like, oh, thank you so much, but it was because I sneezed. But anyway, I'll try to give you non-complicated things so that you can just say, okay, this is coupled to this is coupled to this. I'll separate out the geminal things just to make things clear, but know that in lab it could be complicated. All right, that's our proton NMR. Now we have our carbon NMR. So here, again, these are, each carbon can pull away electron density from the other carbon of the alkene. They're both sp2 hybridized, so they're going to pull away electron density from one another, which is going to help them to be deshielded. So 100 to 160 for alkene carbons. And then we also have allylic again, where, remember I told you that allylic carbon, one carbon away from the double bond, that is going to be deshielded. But it's not super deshielded. So here, if it's a secondary, so a CH2, and this is a CH2, look at where this would be 20 to 30, and this is 20 to 40. It's not really that much different, but it's different-ish. But, you know, this is way more dramatic, right? 100 to 160. That's obviously much different, but we get some difference there. We're moving downfield if it is allylic. So if we have our different carbons, you can see here 122 for these carbons that are sp2 versus for the carbons, the analogous carbons that are sp3, 34. Here we have the allylic carbons, so 18.9 versus 19.2. It's not really much to talk about there. There's not really a lot of difference, but there's a little bit of a difference, let's say, in something in other molecules, but here we're not really seeing that much of a difference. But anyway, here we have 123 and 132 for these two carbons that are sp2 hybridized versus 22 and 34 for the analogous alkane. Again, for the two allylic carbons, they're not that much different than what we would expect. So you might not see that much. I might try to make it a little more obvious when I'm giving you an exam question, but it's not really, you're not really going to see that much allylic there. But anyway, questions on carbon or proton NMR? All right, moving on to IR. So for your IR, you already knew about this, right? We said right below 3,000 we had alkanes, and right above 3,000 we have alkene, and it is the carbon-hydrogen bond there specifically. So that's telling you that you have a hydrogen on your alkene carbon. And then we also have down here between 1620 and 1680, typically, these are typical ranges. Sometimes they can be a little high. But anyway, we have this value that's telling us that we have a carbon-carbon bond. So that is stretching carbon-carbon for 1620 to 1680 versus carbon-hydrogen. That stretches 3050 to 3150. So we already knew about this, but now we're just reiterating something that we already knew, adding into our knowledge about the IR. Questions there? Okay, so now we have something else. So when we get into an NMR problem, you know, one of our long NMR problems where we have the data, the IR, proton NMR, carbon NMR data, now you're going to be using your molecular formula to do another thing. You're going to be calculating degree of unsaturation. So whenever you get an NMR problem from here on out, on the problem sets, on the exams, you're going to calculate degree of unsaturation with your molecular formula. So before I just gave you the molecular formula and it didn't really mean anything other than to say, you know, this isn't a carboxylic acid because we don't have two oxygens or whatever. Now we can use it to figure out something called degree of unsaturation. Online or in other textbooks or whatever, people call it the index of unsaturation or IOU. But those are the two values that I've seen it referred to as. But anyway, we have this equation that you definitely want to mark, put in your notes. If I let you have notes on an exam, this is something you want to have with you, right? Mark so that you can do this calculation. But it's 2 times the number of carbons plus the number of nitrogens minus the number of hydrogens minus X. What is X? The halogens. And always plus 2. Always make sure you do plus 2. And then everything is divided by 2. That gives you your degree of unsaturation. So here we just have C5H8. So 2 times 5 minus 8 plus 2, because always plus 2, divided by 2. And so here we get 2 for our degree of unsaturation or index of unsaturation. Yeah, whenever we have an NMR problem, we're going to do this. And so why do we do this? Because this gives us information about the unsaturations that are present. And so what are unsaturations? Those are going to be rings or pi bonds. Rings or pi bonds. So what did we say? A single bond is a sigma bond, but we said a double bond has a sigma bond plus a pi bond. We said a triple bond is sigma plus pi, right? So what we're talking about here are these pi bonds. So here for C5H8, 2 pi bonds. So we can have 2 pi bonds, so 2 alkenes. Are we going to use it for alkanes? No, because if you can use it, but it tells you the answer would be 0. Or if it is 1, then that tells you you have a ring. But you can use it for alkanes or anything. But anything that I've given you before, we didn't really need it because it was always a straight chain alkane. But now we're adding in alkenes and we can do rings and things. So now we're going to use a degree of unsaturation for all of our NMR problems. But anyway, an index, a degree of unsaturation of 2 tells us we have 2 pi bonds or 2 rings. We could have 1 pi bond and 1 ring. So we have all these different combinations. Pi bonds could also be 2 pi bonds from an alkane. An alkyne. So we have all these different things that we can do with this too, but that gives us a little bit more knowledge as we are doing our NMR problem. We are ignoring oxygen and sulfur when we do these. There's no oxygen or sulfur in the equation for degree of unsaturation because they don't change the unsaturation for the molecule. So here's some more. We have C16H14, degree of unsaturation, if you do that math, is 0. And so we have here this straight chain alkane, and then you have a bunch of different isomers where you can do branching and stuff like that, but they've just shown you one kind of representative structure, but no ring, no pi bond. If you have a degree of unsaturation of 1, you can have either a pi bond or a ring. You can't have both. If you had 2, then yeah, you could have 2 pi bonds, 2 rings, 1 pi bond or 1 ring. If you have 3, then now you have different combinations, right? 3 pi bonds, 2 pi bonds, 1 ring, 1 pi bond, 2 rings. You could have 3 rings. All these different combinations now when you have these different degrees of unsaturation. But obviously your degree of unsaturation gives you one piece of data. Then you use your IR to figure out what those unsaturations are for your molecule. And you'll see this when we get to our problems later in the end of this chapter. So let's do an example with this. Degree of unsaturation for this molecule. So C8H10 BRNO. So our degree of unsaturation, 2 times 8 for the number of carbons. We have 1 nitrogen, so plus 1, minus the number of hydrogens, which is 10, minus X, remember X is the halogens, and we have 1 halogen, so minus 1, and then plus 2, all over 2. Now, some of you guys can do math in your head, and that's great, but I've seen a lot of people have 2 plus 2 equals 2 on an exam, so I would say have a calculator near you just to do this simple math, but go ahead and tell me what the answer to this is in the chat, please. Yep, it's 4. So if you got something other than 4, check your math. But yeah, this is 4. So feel free to do it in your head, but just know that when you are stressed out, a lot of times your mind will do math and then do it again. And you'll be like, why did I get the wrong answer? It's because you were too smart. So maybe just get a calculator to calm those nerves. So when we are in lab also, when we do our learning assessments, you probably want to have a calculator with you in case you need to calculate degree of unsaturation. All right, questions on that? I guess I should say, what could this be? It could be 4 rings. It could be 3 rings and 1 pi bond. It could be 2 rings, 2 pi bonds. It could be 1 ring, 3 pi bonds. It could be 4 pi bonds. Right? We have all these different combinations of what we have there with these 4 unsaturations.
Dr. Nalbandi,
Yeah.
do we have to worry about triple bonds?
Right now, no, but yes. But don't let it keep you up at night right now, no. But yeah, a triple bond would be 2 pi bonds, right? So there could be an alkyne here, and then 2 rings for this molecule. That's one possibility. Or it could be 2 double bonds and 2 rings. So there's a bunch of different molecules that we can draw with this molecular formula. Again, going back to what we said in lab, this is why we draw the molecule in organic chemistry, because we have so many different possibilities for what this molecule could look like. With this many atoms, there's just a lot of possibilities there. All right, moving on now. This is 11-5. Oh, I should have said the IR stuff was 11-8. Then degree of unsaturation was 11-11. So we skip to the kind of the end of the chapter. 11-11 for degree of unsaturation, 11-8 for IR. Now we're back to 11-5 for a reaction now. All right, so our reaction with the alkenes, we said alkenes have these pi bonds, they're unstable, so this is very reactive. What is one reaction that we can do? We can do what's called a hydrogenation. So we take an alkene, and we know alkenes are unsaturated, and then we hydrogenate it, where each carbon of the alkene gets a hydrogen. So remember, this is H2, hydrogen gas, gets hydrogenated, where then we end up with the alkane, which is now saturated. So we go from something unsaturated to something that is saturated in the course of this hydrogenation reaction. We have to use a catalyst. So for a catalyst, we can use palladium, we could use platinum, we could use nickel. So we have various things that we can use. So when we are looking at these, oops, sorry, I skipped a slide. So for hydrogenation reactions, they are very exothermic, so we can release heat here. And so we are releasing heat. That heat is called the heat of hydrogenation. And so every time we have a double bond, it's about 30 kilocalories per mole that's released for every double bond that gets hydrogenated. So the heat of hydrogenation is the heat released as we take an alkene and turn it into an alkane, as we go from an alkene to an alkane. So as we saturate this, as we hydrogenate this. So looking at this now, we go from something unstable. Here we have various alkenes. So we have 1-butene, 2-butene, 2-butene, cis versus trans. And we're changing them into butane in this hydrogenation reaction. So we start off with an alkene, and we go to an alkane. The alkane is lower in energy. It's more stable. And so with it being more stable, why is it more stable? Well, because we have these 2 carbons and they're sharing 4 electrons between them. So we have a lot of electron density between the 2 carbons, which makes this unstable. It wants to break this double bond and turn into an alkane, where now we only are sharing 2 electrons in between 2 carbons. Remember, electrons repel. So trying to have 4 electrons in this small space is going to repel. So unstable for the alkene versus the alkane. There's only 2 electrons in that space, so now it's a little bit better. So when we do the hydrogenation, we're always going to go from an unstable alkene, or a less stable alkene, I should say, to a more stable alkane, which is butane. All of them are going to form butane. So if we look at the amount of heat that is released, that gives us information about the stability, right? More heat released means that it was higher in energy to begin with. So here, if we're releasing 30.3 kilocalories per mole, that means that the starting material is higher in energy than if we're only releasing 27.6, right? More heat released means that this was less stable to begin with. So the least stable releases more heat. And the most stable releases the least heat. So as we look at this, now we can see what is more stable. More stable is trans-2-butene. Trans-2-butene is more stable than cis-2-butene, not by a lot, only 1 kilocalorie per mole. And it's also more stable than 1-butene, again, not by a lot, by about 2.7 kilocalories per mole of energy. but we can see more energy is released when we hydrogenate a less stable alkene. So this gives us some information about stability of alkenes. So first of all, cis versus trans. Trans is more stable. Why is this true? Why is trans more stable than cis? Well, think about steric hindrance. So based on sterics, we can see that if we have cis, now we have these two large groups that are trying to occupy the same side. We can't rotate around a double bond, so we have these two large groups trying to occupy the same space. So we get a lot more steric hindrance than when we have the trans, where now we have a large group and a hydrogen on the same side, and a large group and a hydrogen on the other side. So trans is more stable than cis based on sterics. Now, I also want to point out to you that with this molecule, as they've drawn it, we don't do wedge dash for sp2 hybridized carbons. I'm going to write that over and over again on every single one of your molecules where I see wedge dash on an sp2 hybridized carbon. We do wedge dash for sp3. Here they're doing wedge dash to show you this is pointed toward you, and these are pointed away from you. But when we draw an alkene, we usually draw it within the plane up and down rather than here flat. So they've taken a molecule that we usually draw up and down and they flattened it so you can see something's coming toward you, something's moving away. Don't do wedge dash. Don't do how they've drawn it here. Draw it how you see it down here with the cis trans all within the plane of the page, up and down. So we see that our trans is more stable than cis. But then we can also add in the other things. So as the substitution increases, stability of the alkene also increases, right? When we were looking at that butene, we had butene that was so I'm going to go back. Oh no. My computer died, so give me a second to get back going again. I have to get this stuff going. Give me a second. So just to finish up what I was saying here, it's not letting me get back onto my onto PowerPoint. But anyway, we have our carbons here that have nothing on them. So based on hyperconjugation, there's no substitution at all on there. So this is our least stable. Once we add in an R group, then we have an alkene that's a little bit more stable, adding in one R group. If we add in 2 R groups on that carbon, then it's slightly more stable, but we still have a carbon without any R groups on it, any carbons on it, based on hyperconjugation. Remember hyperconjugation, donating an electron density into that bond through those carbons that are bonded to the carbon of the alkene. So then we go from there to our cis alkene, which is better than having 2 carbons on the same carbon. Now we have them on different carbons. And then we have our trans, which is more stable based on sterics. So then we go from our 1,2 disubstituted. This was our 1,1. We go from our 1,2 disubstituted to then more stable being our trisubstituted. And then a bit more stable than that being, because of hyperconjugation, just like what we said before when we were talking about the radicals, based on what we were saying before when we were talking about the carbocations, more R groups donating in electron density will stabilize the p orbitals of this pi bond. So we want to have our most stable will be the one with the most R groups on it, which is tetra substituted. All right, so we have the least stable here with only hydrogens on it, all the way up to our most stable, which is tetra substituted. All right, so that's where we're gonna end. We have an announcement today. Go ahead, you guys unmute yourselves.
Hi everyone. So for Health Science Society, it's just like the club fairs this week. So if you guys are interested in joining, you can click the link. We put it in the chat. And I'll also put our Instagram in there too as well. If you guys are interested in following us, we're gonna post a lot of updates about upcoming events and all of that kind of stuff. So we're gonna be having, our club is based on like events. So we're gonna have Princeton Review come in and Western University, and we'll also have an opportunity for a practice MCAT and GRE coming up this semester. So if you guys are interested in that, we'll be like sending out emails throughout the semester about all of that kind of stuff. And if you guys have any other questions, you can just like DM us. We'll usually get back pretty quick. And yeah, if Josh and Brittany, they're also in Health Science Study, if you guys want to add anything, that'd be great too.
No, I think you covered everything.
Oh, sorry.
Oh, no, go ahead.
You can
Go ahead,
DM us through our Instagram that's in the chat. Just letting you know and clarifying that.
I have nothing else to add. You guys are great. Thank you.
All right, you guys. So that's their announcement. If you have any questions, you can, for me, you can stick around. I have a little bit of time, but if you don't have questions, make sure you're doing the reading. Make sure you're doing the homework. Oh, Ahmed wants to make an announcement. Go ahead.
Hi guys, I'm Ahmed, and I'm the Vice President of Pre-SOMA, which stands for Pre-Student Osteopathic Medical Association. If you guys want to join our club, I'm going to give you our Instagram handle. You can go and join it. So basically, this is centered towards those who want to pursue the DO degree, which is the legal equivalent of an MD. Both are medical doctors. And if you want to know more about the degree, you don't want to miss out on 39 medical schools. So you really want to know more about this. Please join us. We also host kind of like Health Society. We have practice MCAT people, and Western University has a medical school. We are soon going to bring them in our campus as well. So if you want to know and make more connections with people who are in medical school, you might want to join our club. See you there. Thank you very much.
All right, you guys. Have a great, oh, you guys are sweet. Have a great weekend. I love you guys. Be safe out there. And then make sure you're doing your homework and you're reading. Make sure you're, organic chemistry is keeping you awake at night. That's what it does to me. So hope it does it to you too. Bye, you guys. Have a good weekend. If you have questions, stick around. You're welcome. Bye.
Thank you.
Anybody have any
Thank you.
questions?
Dr. Nalbandian,
Mm-hmm.
I'm wondering why